Okay, so we have what are called transformations. So you know that word in everyday life, not just math, right? To transform means to like change it in some way. Okay, so the transformations that we want to go over are first called a reflection. Okay, so let's go ahead and define what a reflection is or describe how it works. In a reflection, every point moves an equal distance to the other side of what's called the line of reflection. Okay, and then we'll do an example of a reflection. Okay, so let's say that we're going to take the graph that's given to us and we're going to reflect over the x-axis.
So if I'm guessing, you're gonna go to four positive four and down to six kind of like the way
Sorry, you said go to +4 and then to -6? Is that what you said? Okay, very, very close. You you reflected over the y-axis. Okay, so here we're going to do the x-axis. So that's this one. It's the horizontal line. Okay. And so according to the definition, every point moves an equal distance to the other side of this line of reflection. Okay, so let's take this point right here, the one I'm drawing a dot in. Right now, that dot is how far from the line? It's 1, 2, 3, 4, 5. It's 6 units away. Okay, so you move an equal distance to the other side. Okay, so instead of being 6 above the line, now you flip it down to make it 6 below. Okay, so from that same point, you go down 1, 2, 3, 4, 5, 6, and that's where that point goes. Okay, so again, reflection, it's the same number of units, but on the other side. Okay, instead of 6 above, it's 6 below. Okay, and you can repeat the next point I see right here. Right, this point is currently 1, 2, 3, 4 above. So you go 4 below. 1, 2, 3, 4. That's where that dot goes. Okay, and then I'm gonna at this point in pink, just 1 to 2 above. So you would go 2 below. This next one's interesting. The next dot is already on the line of reflection. So when that happens, it doesn't, it's, I guess you could say it's like 0 above, but that means you go 0 below, so it doesn't go anywhere. Okay, so if it's already on the line, it stays where it is. Okay, but now we start below, right? This line has a point that's 2 below. So that would flip 2 above. Okay, so that's enough points for us to see what's happening. Again, the original points are on the actual line, but the new points we've been drawing, we can now connect them up. Okay, so yeah, in pink for me, is the reflection. So visually, you can think about it. If you were to flip this red line upside down, right, this would go here, this would go here, this would go here. But the part below would flip up, right? This goes here, this goes here, this goes here. Okay. So again, you just take individual points, you move them an equal distance to the other side, and once you've done enough, you connect up the new points. Okay, the next type of transformation is called either a vertical stretch or a vertical compression. Okay, so how this works. Every point's y value is multiplied by the same number. And that number is called the scale factor. Actually, let's just call it the factor for now. Okay, so let's do an example of this. Let's do a vertical stretch by a factor of 2. Okay, so what we're going to do is we're going to pick a point on the original line, and we're going to multiply its y value by, for this problem, 2. Okay, so for example, this point right here, it's currently at 4, 3. It's 4 right, 3 up. Okay, because the problem tells us to do a vertical stretch by a factor of 2, we're going to multiply only the y value, not the x value. We're going to multiply the y value by 2. Okay, so instead of 4, 3, the vertically stretched point is now at 4, 6. Okay, same thing over here. This point is currently at 2, 2. Keep the x value the same, but multiply the y value. Okay, so the new y value is 4, so 2, 4 is the new point.
What if it's 0?
Good question. We'll get to that in just a second. Yes, exactly. Okay, so 0, 1, this point right here becomes 0, 2. Okay, and so here's a point, like Dominic asked, what happens when it's 0? So this point is currently at -2, 0. It's 2 units left, but 0 up or down. So if you multiply 0 by 2, it's still 0. Okay, so actually this point stays where it is. Okay, but let's now go over here. There's this orange handheld one. Oh, sorry. The y coordinate is -1, right? So when you multiply that by 2, -1 times 2 becomes -2. Okay, so let's go ahead and connect up the new points. All right, so we start here, we go through here. Sorry. Okay, so in green is the vertically stretched version. So again, on the original graph, you pick a point. There is, for this problem, it was 2. It could be other numbers for other problems. So again, you keep x the same, you only multiply the y. Okay, and then the last one we're going to talk about is called translation. So with a translation, there's no multiplying. Every point is moved an equal distance.
So you're saying there's like some might be good at and there's the other thing.
Exactly. So unlike reflection, where some points move downward and some moved upwards, with the translation, every point moves the same direction. Okay, so you often describe a translation as sort of like sliding the graph around. Like if you imagine you cut this out and then you just dragged it around, right? That would be a translation. Okay, so as an example, let's take the current graph and translate it 3 left and 5 up. Okay, so the good news is you don't need to move every single point, just a few key ones. Okay, so like you don't want to try to move this point because this point is not on the grid. It's not at a whole number, so we can't really work with it easily. But this point right here at 1 comma 0, that point is on the grid. It's where 2 lines cross. Okay, so let's go ahead and move that. We want to move that point 3 left and 5 up. Okay, so this point will end up right here. Okay, and we just repeat for a few more points. Okay, so again, look for a point that is on the grid. So all the way over here at -1, -2, there's another clear dot. Okay, and again, all points move 3 left and 5 up. Okay, let's try to find 2 more. At the bottom, 3 left, 5 up. Okay, and one more. All the way on the right, 3 left, 5 up. Okay, so now you look at the new points and you just connect them back up. Okay, so we'll go and draw the circle that goes through those 4 points. Okay, so yeah, the shape stayed the same in this case. It just moved to another location. Okay, so now you know how to change a graph, but let's try to identify what change happened when you're given both the starting and the ending versions. Okay, so if you look at the 3 problems below, there's 2 graphs, right? There's the dashed red graph and then the solid blue graph. Okay, so in all cases, you're starting with the dashed red one and you're trying to change it into the solid blue one. Okay, so you're allowed to use any combination of the 3 transformations listed above. Okay, so somehow you need to take this dashed red graph and make it land perfectly on the solid blue graph. Same thing over here. How do you change the red into the blue? And over here, how do you change the red into the blue? Okay, you might need to do more than one thing. Okay, so go and take a minute and see if you can write down how to change the red graph into the blue graph. Again, the red graph is changed into the blue, so we're starting with the red. Okay, so here you sort of notice the graphs are the same shape, right? They're not like one's taller than the other. One's not upside down. So that means it's going to be a translation. Okay, so again, the whole graph just slides around, right? That's what a translation is. But it's easiest to do if you just look at the vertex. Okay, so the vertex of the red graph is at 0, 0. The vertex of the blue graph is at 2, 1. Okay, so to get from the red to the blue, you go 2 right and 1 up, or 1 up and 2 right, either order. Okay, so now for the middle problem. So here it's not just a translation because you can see the blue graph is skinnier than the red one, right? We know that with translation, the shape stays the same, but here the shape is different. Okay, so you're right that it's going to be that vertical stretch or compression. So I haven't explained when to use stretch or compression yet. I'll do that shortly. But yes, what happens to the y values? So like this point is at 1, 1. That same x value on the other graph is at 1, 3. Okay, and then if you look into the negatives, let's see. Well, that's actually really the only point we can use, right? We can go over here also. -1, +1. That point becomes -1, +3. Okay, so how you get from the original y to the new y is you multiply by 3, right, in both cases. Okay, so yeah, this one will be called a vertical stretch. Exactly. Okay, so yeah, I'll just tell you right now that whenever the factor is more than 1, you call it a stretch. So stretch by 2, stretch by 3, stretch by 5. You call it a compression when it's a fraction. So we'll see an example of that later. Okay, and lastly, how do we get from the red graph to the blue graph? Well, first thing you notice is that the blue graph is upside down, right? So the only way to flip a graph upside down is through a reflection over the x-axis. Okay, so if we were to just flip it upside down, it would look like this. Yeah, so you have to do two things. First, you reflect it over the x-axis, then you translate it right 1. Okay. Okay. So questions on any part of uh, what we've covered so far? Okay, let's please turn to the back. Okay, so here's something that you guys need to know. So this phrase, whenever we talk about the parent function for quadratics, okay, so that means sort of like the starting point. The most basic quadratic function is just y equals x squared. And from there, you can perform various transformations on it. Okay, so the version over here is vertex form, right? We've learned this one before. Okay, so A, H, and K tell us not only the vertex, but also additional information. Okay, so let's please write down these effects. Okay, so if the absolute value of A is greater than 1, that means that there is a vertical stretch by a factor of the absolute value of A. Okay, we need the absolute value symbols because if A were -5, you would say vertical stretch by a factor of 5, not by -5. Okay, now if the absolute value of A is between 0 and 1, that means there's a vertical compression. Okay, so compression means making things smaller. So that's why you do it when the number is between 0 and 1. Okay, and then lastly, if A is negative, that means that you reflect over the x-axis. Okay, so yeah, A does all of those things. If A is negative, that means you've reflected over the x-axis, which essentially means you flip it upside down. And then if A has a number that's not invisible 1, you either vertical stretch or vertical compress. Okay, so the good news is it's only A that's that complicated. H and K are simpler. Okay, so first H. Okay, so when H is positive, that means you translate right. Okay, now the tricky thing is H is always the opposite of what it looks like. Because just like with vertex, right, we know that because it's x minus H, the minus sign is part of the formula. Okay, so we'll do more examples of that later. But then lastly, but we're not going to write it, but the opposite is true. When H is negative, you translate left. Okay, so similarly, when K is positive, you translate up. And again, you don't need to write it, but the opposite is true. If K is negative, you translate down instead. Okay, so yeah, problems can have any combination of these things. Okay, so one note, one thing you want to be uh, careful about. We'll say to be safe, always translate last. Okay, so it's kind of complicated and we don't need to get into the reason, but sometimes it's okay to do the translation before your vertical stretch or reflection. Sometimes it's not okay. But to be safe, if you always translate at the end, you'll never get it wrong for that reason. Okay, so yeah, always do translations at the very end. Okay, so let's do an example of identifying the transformations without a graph like on the front page, but instead by being given an equation. Okay, so here's a complicated looking equation. F of x equals 3 parentheses x minus 4 close parentheses squared plus 2. Okay, so I want to know how the parent, which again is y equals x squared, how was that most basic function changed into this one? Okay, so the way we approach this is we identify A, H, and K. Okay, so you've done this before. You've done this in unit 2. So remember, it's A parentheses x minus h squared plus k. So for this problem, A is going to be positive 3. H is, again, the tricky one. H is positive 4. The minus sign is part of the formula. So even though it looks like minus 4, H is actually positive 4. But K is what it looks like. K is positive 2. Okay, so how does knowing A, H, and K help us identify the transformations? So look at A first. Okay, so actually I'm going to start down here. Okay, if A is negative, reflect over the x-axis. A is not negative, so we skip that. Okay, next, if the absolute value of A is greater than 1, there's a vertical stretch by that factor. So yes, A is greater than 1, so we have a vertical stretch by 3. Okay, so that's the first thing. Okay, so again, that's from the fact that A is 3. Okay, now we can look at H. So when H is positive, translate right. So since H is positive 4, we're going to translate 4 right. And then K controls up and down. So K is positive, so we translate 2 up. Okay, so let me show you visually what we mean when we say like, oh, make the transformation. Okay, so I'll show this again in a second if you're still writing, but okay, so here's the parent function, just y equals x squared. Let me make it a little bit bolder, easier to see. Okay, so the second graph I gave you was y equals 3 parentheses x minus 4 squared plus 2. Right, so I wanted you to change the red graph into the blue graph. Okay, so what I said is first vertically stretch it by a factor of 3. Right, so take the original graph and stretch it out. Okay, so the red graph turns into the green graph, right? You stretch it out. Then I said translate it 4 right. So you take this and you move it 4 right. And then lastly, you take that and move it 2 up. All right, and you see it lands perfectly. Okay, so yeah, it was a 3-step process. First, we vertically stretched it, then we moved it right, then we moved it up. Okay, but then that makes the original graph land on the new one. Okay. So go ahead and try the problem right next to it, please. Okay, so same strategy, identify A, H, and K, and then based on that, use the description above to identify the transformations. For g of x over here, A would be the invisible negative one. H is not positive 5. H is negative 5, because remember, it's got to be x minus h. And K is invisible 0. All right, so again, H and K are invisible zeros if they're not there, but A would be invisible 1 because A multiplies while H and K add and subtract. Okay, so when A is negative 1 or positive 1, there's no stretch or compression, right? Because there's no or equal to. So there's no vertical stretch or compression, but A is negative. Okay, so that means that we reflect over the x-axis. Now we look at h. H is negative 5. Okay, so when h is positive, you go to the right. So here it's the opposite. When h is negative, you translate to the left. And then, k is 0. Well, that means you go 0 up or down, so you don't need to write it. Okay, so yeah, just 2 steps for this one. Reflect over the x-axis and then translate 5 left. Okay, so what you have to be careful about is you need A, H, and K. You cannot use A, B, and C for transformations. Okay, so when you look at this problem, 4 is not H, and 7 is not K, right? That would be in standard form, A, B, and C. Okay, so you need the form with parentheses and the squared. Okay, so how do we turn this to vertex form? We've done this before. The method we'll use is we'll just do the axis of symmetry. Again, right now, A is invisible 1, B is 4, C is 7. Again, B and C are not helpful for the transformations. We need H and K, but we'll go ahead and use B and C for now, or I guess just B. Okay, so negative 4 over 2 times 1. Okay, so negative 2 is your axis of symmetry. And now to get the y value of the vertex, we substitute that x value in here. Okay, so x squared becomes parentheses negative 2 squared. Plus 4x becomes plus 4 times negative 2. And you still have the plus 7 at the end. Negative 2 times the second negative 2 is positive 4. Positive 4 times negative 2 is negative 8. Add and subtract from left to right. 4 minus 8 is negative 4, plus 7 is 3. Okay, so that means the vertex is negative 2 comma 3. Okay, so we're not done yet, but let's see if there's any questions on how the vertex was calculated. Okay, so now that we have the vertex, it's very easy to get vertex form because the x coordinate of the vertex is h and the y coordinate of the vertex is k. Okay, so now we can fill in the y equals a parentheses x minus h squared plus k. Right, we already know from earlier that a is 1, so we don't need to write that. X minus h, we now know that h is negative 2. Okay, so it's x minus negative 2. Keep the parentheses, keep the squared, and then plus k at the end. We now know that k is 3. Okay, but instead of saying minus negative 2, we can just write plus 2. Instead of subtracting, you add the opposite. Okay, so yeah, the vertex form would be this. Okay, but now putting all the letters together, A was 1, H was -2, and K was +3. Okay, so notice we don't use the 4 at all. The 4 is not part of any transformations, and neither is the 7. Okay, so A is 1, that means no vertical stretch, no vertical compression, and no reflection, because it's positive. Okay, so for this problem, we skip A, but H is -2. So we know H is left and right. Because it's negative, that means left. Make sure you don't say -2 left. The left already takes care of the negative. Okay, and then the K value is +3, so that means you translate 3 up. Okay, so once you have that, please try n of x right next to it. So again, you notice n of x is also not in vertex form. So make sure you start by converting it. Translate 2 up, so those 2. So where does this come? Yeah, so the tricky thing is A is the only number for 1 because A happens to also
I split the K difference.
no. If there's no H, it's actually 0 because it's not 0 when it's in the bottom of x. So the answer is not 0, but H is 0, which means that it would be x in parentheses x is 0, but that would be simple bottom. So yeah, means that like -0 part. Once it gets that. Convert, and that's the vertex form first. Yeah, I think that's a symmetry.
Actually, love theory. I know this is
You want that number to propose. Yeah.
We can have it back there too.
1 half is not the same as 1 plus 5. It's not 1.5, it's just 1 half. So yeah, 1/2. What calculation are you doing now? This one's weird. Hold on, try. Will you type it in a little bit quickly? So in here, A is not negative, we can decline. Absolute value of 1 half is still 1 half. So it's not bigger than 1, so it's not good. But 1 half is between 0 and 1. So we call it a Bernoulli expression by the that. Yes, and then now we're your axis of symmetry, you have the right formula here, but notice B is -4. So when you do -4, it goes to positive.
You get it? Yeah. Why did you say those?
The only thing is your theta value. Right here, -4.4. Yeah, if you think you know what to use and go on to that. Okay, so this is in standard form, there's no parentheses. But in order to know the transformations, we want vertex form. So it goes from this form to this form. Our first step would be the formula.
So.
If you have so we convert the 2 into 2/1. Oh, but now the 5. Draw the fraction bar. Okay, so now multiply fraction. 5 to the cross. So 1 times 2. One more negative 1. Well, the 2/2, you're dividing by so the whole denominator simplifies to 1.
Okay.
So you solve the raw part, which is right. Okay, so the x value is 4. Yes. Okay, you apply that.
Stop reading. Is it like somehow?
So those are your that is the vertex or negative one. So that's also the so eight is four and something is negative one. Okay, so now we have enough info to. So remember first we look at A. So was A positive? Or sorry, was it? So we can skip. There's no reflection over the x-axis. Right. Well, we're still on A is 1.5 bigger than but 1/2 is between 0 and 1. So we say there's a vertical compression by the vertical compression by yeah. Even though it's getting bigger, it's getting okay, so we're done with A, but we gotta do H next. So H is positive 4. So what is it positive? Translate that in units of B. So the problem for the opposite direction.
What do you have to write down?
And then K is negative 1. So what is this? Yes, Now,
Yeah.
oh, I see. Let's see if I So the A value also has a translation.
Okay, let me go ahead and ask for quiet so that I can go over this one and then we'll do a problem from the last section. So for n of x, again, this is currently in what we call standard form. There's no parentheses. So this is A, B, and C, which is good for like the y-intercept, right? You know, the y-intercept is 7, but it's not good for transformation. Okay, so let's do the axis of symmetry formula. X equals negative b over 2a. Negative b becomes negative 4. And 2 times a becomes 2 times 1/2. Okay, so up in the numerator, negative 4 is positive 4. In the denominator, 2 times 1/2 is 1 whole. So 4 over 1 becomes 4. Okay, so 4 is the x coordinate of the vertex. And now we plug that in to get the y coordinate. 4 squared is 16. Half of 16 is 8. Negative 4 times 4 is negative 16. 8 minus 16 is negative 8, plus 7 is negative 1. Okay, so the vertex is 4 comma negative 1, which means that h is 4 and k is negative 1. And we already know from back here that a is 1/2. Okay, so now that we know a, h, and k, we're ready to write the transformations. A being 1/2, which is between 0 and 1, means we say vertical compression, not vertical stretch. Okay, and then h being positive 4 means that we translate 4 right. K being negative 1 means we translate 1 down. Okay. All right, so again, sometimes the problem will already be in vertex form. In that case, you get to just quickly identify A, H, and K. If it's in standard form, you need to convert it to vertex form to find A, H, and K. Okay, so questions on any of that? Okay, so this last section is just really more of the same, but this time it's taking a sentence and turning it into an equation. Okay, so right here we see translate 5 left. Okay, so we know that left and right is h. Positive h goes right, so negative h goes left. So if you're translating 5 left, that's telling you that h is negative 5. Okay, and then the next part, translate 4 down. That means that k would be negative 4. Okay, so now you just fill in the vertex form with those values. Okay, so again, you always start with y equals a parentheses x minus h squared plus k. This problem said nothing about vertical stretch, nothing about vertical compression, nothing about reflection. So a is invisible 1, you can ignore it. But x minus h becomes x minus negative 5. And plus k becomes plus negative 4. Okay, and now we can just clean it up a little. Instead of minus negative 5, we say plus 5. Instead of plus negative 4, we say minus 4. Okay, so yeah, it's really all the same things, just turning the words into numbers. Okay, so yeah, go ahead and try the last section. If you think